Hello and welcome to video 1 for Math 241 at the University of Oregon. My name is Mike Price. I'll be your instructor for the term. Here is your textbook, Calculus for the Business, Economics, etc. This is the brief edition, although if you manage to get the expanded edition on the cheap, then that's fantastic. That'll work just fine. It has additional content that we don't get to in Math 241 or 242, so it'll work out great for you. Our first section is functions. That's 1.1 from the text, so it should be pretty easy to remember. Here are our learning objectives. In this first video, we're going to accomplish the first one, identify domain and range of a function and evaluate a function from an equation. So, first, the definition. You may have seen definition of a function in a previous course. Ideally, you have because College Algebra Math 111 is a prerequisite for this course, and in that course, function is defined. But by way of review, function consists of a set of inputs, and that is the domain, a set of outputs, which is its range, and then a rule, which has this special condition on it. So the rule connects inputs to outputs, but it has to do so in such a way that an input is guaranteed to go to exactly one output. So perhaps a real-world example of this is that if you put bread into a toaster, so bread is your input, the function machine is the toaster in some sense, and then the output is the toast that you would get. Now, if you imagine that you put in bread and then you have to wonder whether you're going to get toast or jam out of your toaster, that's not quite the predictable machine that we would hope. So if you have a function, it must be that given a particular input, you know exactly what output would come out. So we put in bread, we get out toast. Consider another real-world, similar example perhaps, an incinerator. If you give an incinerator some input, it's basically going to always return something like ash, basically, when you're done. So you put in a chair, you get ash. You put in a table, you get ash. And it seems like that might violate this condition, this uniqueness condition on a function. But that actually doesn't. It's still a predictable machine. If you put a chair in, you know what's going to come out. If you put a table into the incinerator, you know what's going to come out. The fact that what came out is the same for both of those is not a problem. It's still a predictable machine. Another informal example, perhaps, we might say the quality of a coffee is a function of its price. So here, what we're really saying is that if you want to know what the quality of coffee is, you could use its price as an input. Now, you could certainly argue with that statement, but if we believe it's to be true, just for the sake of argument, price is our input here, and then the quality of that coffee is the output. And how that quality is represented could vary a lot. Given that this is a math class, we will probably be representing these things by numbers. So maybe an expert assigns a scale of 1 to 10 to the quality of the coffee. But it could be something much more qualitative. It could be that the coffee is awful, poor, average, good, or excellent. There's nothing that constrains a function to only being working with numbers, but again, since we're in a math class, we will most likely be working with numbers. So here we're saying that the price uniquely defines the quality of coffee. If you know what the price is, you definitely know its quality. Quick example that's more of a mathy disposition. So we've got an equation, y we could view as the output and x as the input. And then the rule here, since it looks like 3 times x plus 1, written in words, that would be triple whatever your input is, that is multiply it by 3, and then add 1 at the end. With a specific value of x, you could say at x equals 2, then here's our output. Y would be 3 times that x value. Now that's 2. And then we add 1 to that. So here's our tripling our input. We add 1, and of course that's 7. And then a note, of course, if we give a value of x in this case, we're not going to have to guess at multiple y values. There won't be multiple values that come out the other side. So we put in 2, we for sure get 7 out of this function. So a slightly more involved example. So this function is, as you can tell, more complicated than the one we had before, but it's similar in that it's defined by some expression. X minus 3 in the numerator, x squared plus 5 in the denominator. We divide those two things. So we have a few tasks here. Find and simplify f of 5 is our first one. Next is simplify f of x plus 3. And finally, we'll find the domain of this function. First task. So if we want to compute f of 5, all we're really doing is saying we no longer have x as the label for our input. Now we're putting in a specific value, 5. So we go back to our original function, we replace x with 5, and if you recall, here's where our x used to be, right there and right there. So now we're replacing with the number 5. 5 minus 3 is 2 in the numerator. 5 squared is 25, plus another 5 is 30, so great. F of 5 must be 1/15. Given an input of 5, the output is 1/15. So part A is accomplished. Part B, same motivation, but the expression is more complicated. So instead of just 5 for input, now we have this entire thing, x plus 3. And whenever we've got a more complicated expression like this, there's probably going to be parentheses involved, but the motivation is the same. We take our original function, we replace the input with this new thing, x plus 3. Again, just for emphasis. So the parentheses are necessary because however x, our original input, gets treated, so should x plus 3. This is not especially important on top. We could do without the parentheses here. X plus 3 minus another 3, that's the same with or without parentheses. We just get x. On the bottom, though, it's much more important. X plus 3 all squared is very different from x plus 3. Oh, by the way, square the 3. Those are different expressions. Also remember that if you want x plus 3 squared, that's x plus 3 times x plus 3. So that may involve something you have called FOIL in the past. It's just the distributive property, x plus 3 times itself again. So that gives us x squared plus 6x plus 9, and then the plus 5 is just hanging out waiting for us to simplify. So finally, x squared plus 6x plus 14 in the bottom. Another tempting item is that you'd look at this and say, oh, I've got an x on top and x on bottom. I should be able to cancel those. But that's not actually the case. You have an x on top, I don't deny that. And you have x squared on bottom. But these addition signs make things complicated. We have to consider each of these terms separately. X is a factor of this term, so we're good so far. X is a factor of 6x, which is good so far. But 14 does not have a factor of x in it. So that one term makes us unable to cancel out x from top and bottom. And in fact, this fraction is as simple as it gets. There's that statement again. Part C. We need the domain of f of x, and the biggest issue here is worrying about what could go wrong, essentially. We're gonna take the glass half full perspective for functions. We're going to assume that the domain of the function, assuming that we're working with numbers here at all, we're going to assume that the domain is all real numbers unless we find some issue. So some classic areas where this might occur would be with square roots. Taking the square root of a negative number causes you to have a non-real number. And division, which is, I think, the one most important to us here. If we divide by 0, we get something undefined as well. So the greatest concern is division by 0. And that's because our function actually involves division. It doesn't have any square roots in it, and nor does it have any, say, logarithms, which is, if you haven't been exposed to them before, a topic for later in the quarter. So any other input will generate a real number as long as it doesn't cause us to divide by 0. So here's our glass half full perspective. The domain is anything except what makes the bottom 0. So revisiting our function quickly to see what we're up against, there's our original function, and there's our denominator. So x squared plus 5 is what we have to make sure is non-zero. So x squared plus 5, hold that in your head for a second. We'll get back to it. Write the domain. There we go. So again, what we're looking for is just the troublemakers. What possible values of x could cause this expression to be equal to 0? So x squared plus 5 is our denominator. We subtract 5 from both sides. X squared equals negative 5. We take square roots, and trying to be extra careful here, the square root comes with a plus or minus. And that's because when we eradicate a square from a function, square root is almost its inverse. We have to account for the possibility that whatever value of x was under here was negative as well. However, it turns out that this is moot, because when we look at square root of 5, that would be fine. Square root of negative 5, on the other hand, there is no such real number. There is no real number that when you square it, you get negative 5. So actually, since this was the complete list of things that could go wrong, there is nothing that could go wrong. We conclude that because there are no restrictions dictated by the equation, the largest possible domain is everything, in fact. And everything in this case means all real numbers. So to formalize that notion that what we're looking at is all real numbers unless otherwise stated, we'll give this a name. We'll call this the domain convention. So the domain of a function is all real numbers as long as what we get out of it is still a real number. And again, the primary things to look for are division by 0, taking the square root of a negative number, or taking the logarithm of a non-positive number. But we'll review logarithms later on. A quick example of this domain convention. So let's give ourselves a new function because we're probably getting tired of that division one by now. So we'll say t of x, also to make things more exciting, no more f of x's, x squared times the square root of quantity 5 minus x. So the domain of this, before we cut to the chase and reveal this, the thing that could go wrong here is that we have a square root, and the quantity underneath that could be negative. There could be a value of x that would cause this to be a negative value underneath. That's what could go wrong here. There's no division by 0, there's no logarithms, but there is a square root. So what we should do is make sure that everything under the radical, 5 minus x, stays non-negative. 0 is actually fine too. Square root of 0 is just 0. So we're going to go for greater than or equal to 0 here. Solving for x, we could add x to both sides. We'd have x is less than 5. There's our domain. So because the only real numbers to avoid as inputs are those that make the radicand negative, our domain must be all real numbers less than or equal to 5. That's the end of video 1. Our next topic will be the learning objective associated with function composition. Thanks for watching.